Okay, today, welcome to Earth Science. That's not how we normally start. I'm all flustered now. This is serious. Earth Science. Let's just go to sleep. Earth Science time is how it's supposed to start. Ooh, that actually did make me sweat, though. We have to start over. No, it's okay. We'll do it live. Earth Science time. We're talking about minerals today. Minerals. You've heard of minerals. In what capacity have you heard of minerals before? Tell me about what you know about minerals.
They are rock.
This video is sponsored by Bubbler. I'm JK. I do not have video sponsors. But if I did, it would be Bubbler. Other brands are available.
Celsius.
Some are harder than others.
Okay, so minerals, let's be vaguer than that. There are properties of minerals which include hardness, definitely. So there are hardnesses of minerals. So we have a little list of properties there. What else do you know about minerals?
Oh.
I'm going to do already another little arrow coming off this direction, which we're going to talk about. This will be a nice way to break up the lesson, actually.
Is it the step above the most simplest thing in element?
Okay, I think I know what you're getting at, and I like that description of it. So they...
You're gonna like it.
Criteria, let's put that. Criteria of minerals. They have to be... I'm trying to think of the best way to phrase this. They need to be
Inorganic.
Yes, that's true too, but we're talking about this hundreds thing first. So they have to be compounds with fixed. I'm going to put a little squiggle under that composition because you're right that they some of them are. I should actually not put compounds. I should put pure substances. I'm just going to put substances. How about that? That'll be better. So they're substances with a fixed composition. Some of them are, as you say, Hunter, elements. They are specific kinds of atoms. Some of them are compounds, but the compounds are kind of in between what we would in chemistry call a compound with a definitive, with a set proportion of elements, because they can have substitution. So we'll talk about this in a second, but they can, for instance, if it's composed mostly of a silicon tetrahedron like quartz is, one of those tetrahedra could be replaced with an iron. And when that happens in a great enough abundance, then it's rose quartz. It shows up pink because it has iron substituting some of the tetrahedra. So they have a fixed, but with a squiggly line. It's not necessarily or quite fixed because in reality, nothing is pure. And so they're substances with a somewhat or an approximately fixed composition. Now we have another nested thing. Justice gave another criteria. What else do minerals have to be? That's what the word criteria means, by the way. They have to be inorganic. Which means what?
No way.
That's a different one. We'll talk about that in a second.
They
But
are not any.
They're not
formed.
No biotic. You're not.
okay,
Yeah.
Ethan said it the best so far. They're not organic. They're not composed of carbon-carbon bonds. That's what they're inorganic, meaning that they don't. It's not that they can't have carbon-carbon bonds, but they don't have carbon-carbon bonds that form an organic substance. And that's a messy way to describe it. But in science or in chemistry, we agree that organic compounds are those that have carbon-carbon bonds, and the rest of the bonds of the carbon are filled with hydrogens. And so things like acetylene or methane are organic compounds, whereas diamond, even though it has carbon-carbon bonds, is not, because the rest of the bonds aren't full of hydrogens. But someone mistakenly thought that inorganic meant this word abiotic. Abiotic, A meaning the Proto-Indo-European root, or not root, but prefix A means without, or can't have, or doesn't have, or not. But abiotic, the root of this word is life. So not made of life. Not made by living things. And this one's a little bit tricky because something like synthetic diamond, we were just talking about diamond, which in case you didn't know already, diamonds are a mineral. A diamond found out in nature could be chemically and physically identical to one made in the laboratory, but technically the one made in the lab is not a mineral because it was made by human beings. That was biogenic. Biogenic means created by life. We might say abiotic or abiogenic, not made by life. Abiotic means not alive. Abiogenic means not made by life. So a seashell is biogenic. The seashell is not alive, and it was never alive, but it was made by a living thing. The synthetic diamond is biogenic. It was made by a living thing, a human being that was alive. Maybe still is. What else do they have to be? Do you think?
Capable of changing.
No. Everything's capable of changing, so that ain't it. It has to do with what they're made of. So they have to have a approximately fixed composition, but more than that, they have to have that composition arranged how? It has to be arranged in space in a certain way. What do we call that when the way atoms are arranged in space? If it repeats, it's called a? No. You know it.
Yeah. Crystal.
Crystalline. They have to be crystalline. They have to have a repeating pattern. This is how you spell the word repeating. Pattern, pattern. How did I spell it on the objective? We need to write down the objective, BT Dub. Repeating pattern. Repeating pattern of atoms. I actually spelled pattern right on here, and it did remind me that we're going to write down the objective. It also has to be, there's one other thing. This one will be really easy, which is because we ran out of room, so I won't even have to describe it. What else does a mineral have to be? Yeah, solid at room temperature. Now, I'm going to put solid at room temperature. Some people, including my friend Hank Green, you know Hank Green probably from he knows about science. No, not from Breaking Bad. Hank Green from YouTube. I watched a video once where he said that you are a lava monster because ice is a mineral and the molten form of ice is water, which is what you're made of, and so that would be lava. Like the molten mineral ice is lava, and you're made of that, so you're a lava monster, which was kind of a cute thing to say. But I think, and I've heard other people call ice a mineral, but I think we usually in geology agree that they have to be solid at room temperature. I'm not calling Hank Green a liar. There is some discrepancy or some disparity in the geological sciences community about whether minerals have to be solid at room temperature or just if they're generally solid. But usually we say they're solid at room temperature. Now I'm going to go back to the crystalline one real quick, and then we're going to talk about our objective. But the crystalline one is important. I usually wear a necklace. You might remember me from before. This is my sword necklace, but I usually wear a necklace that looks like a crystal, but it's not. It's obsidian, which is volcanic glass, and obsidian is not a mineral because it doesn't have a crystalline structure. So I'm going to provide. So give me an example of a mineral. We've already talked about one, but give me another example. Give me some examples of minerals. What is the one I already said? Diamond. Right, so let's go down the list. Does diamond have a fixed composition or approximately fixed composition? Yeah, a pure diamond would be pure carbon. Is it inorganic? Yes, we already talked about that. It's abiogenic. It was formed inside the earth, not by a living thing. Is it crystalline? Yes, they're arranged in a repeating pattern in space, and it's a solid at room temperature. So a diamond does count. What else? Someone said salt. If we put rock salt. Let's say rock salt. It has a fixed composition, sodium chloride. There might be inclusions of iron or sulfate or whatever, but generally sodium chloride. Inorganic, formed does not have carbon bonds. Doesn't even have carbon in it, usually. Not formed by life. Can salt be formed by life? Yeah, but the salt that we're talking about, specifically rock salt, is not. It's crystalline, and it's a solid at room temp. Amethyst, someone says, which is a kind of quartz. Amethyst has a fixed composition. If we went to mindat.org, I mean, this is a website you should write down, not a sponsor. As far as I know, other brands are not available, but if you went to mindat.org and typed in amethyst, you would find what specific composition something must have to be considered amethyst. It would be SiO2 dot, and it would have some other chemicals that are included in it. Formed not by a living thing, has a repeating pattern in atoms, and it's solid at room temperature. Well, let's do some non-examples. Give me something this list here. This is going to make it ugly and messy. Non-examples. This list here is going to be for each of these categories something that people might think is a mineral, but isn't because it doesn't meet this one. So what might people think is a mineral, but isn't because it doesn't have a fixed composition or approximately fixed composition? Okay, basalt. I like basalt because I'm just going to put rock. what might be basalt is a kind of rock. It's not a joke. Basalt is a kind of rock, but a rock is not a mineral. A mineral meets these criteria, but a rock is a mixture of minerals. A rock is a solid mixture of minerals. So basalt is a rock. It doesn't have a fixed composition. It's a mixture of different compositions. What's something some people might think is a mineral, but it isn't because it's not inorganic?
Coal.
Also, we'll say coal, even though coal is also biotic. I just couldn't think of a better example for something that isn't inorganic. So a coal is an organic compound. We might say, I'm trying to think of anything that is formed, that is an inorganic compound that's not biogenic. No. If we think about, this is kind of a stretch, but like on Titan, on Saturn's moon Titan, there are I think lakes of methane and solid crystals of, I don't know, maybe paraffin or something like that. It's not biogenic. There's not, as far as we know, life on Titan, but it is organic compounds. And if they've met the rest of these, so I'm just bleh. Okay, what's one that people might think is a mineral, but it isn't because it's not abiogenic?
Salt and salt water.
No, that probably is. And no, that's not what we're talking about. And no, that's not even a solid. So let's say apply a different one.
Coal.
Coal, okay, good. Coal. What else? I said shell. No, oil doesn't count because this is not a solid either. The example for crystal I just had was something like obsidian, my little crystal. And it's a little bit tricky because my crystal that I normally wear, it's not a crystal, but my necklace I normally wear is even shaped like a crystal. Someone cut it to look like it's a crystal, but it's not. It's glass. Thanks, Ethan. And then give me an example of one that's not solid. I'm going to put that one ice. I'm going to just say it. Hank Green's not wrong necessarily, but most of us agree that ice is not a mineral because at room temperature it's not a solid. Okay, so these are what something has to be in order to be considered a mineral. What are some other properties of mineral? I'm going to scooch this one over so it's over here. What are some other properties of minerals? And I'm also going to do it in green.
Or Hank.
Yeah, out of respect for Hank Green. What was the property that we just had up there hardness. And the nice thing about these properties is that these are not how we determine something is a mineral. That's these. These are how we determine whether it is this mineral or that mineral, what the differences between the minerals are. So hardness, there's a thing called the Mohs scale of mineral hardness. Mohs scale of mineral hardness. Nice job. I'm going to try to find a little diagram of the Mohs scale of mineral hardness for you. Here is the Mohs scale of mineral hardness. Is that showing up on the camera, Carson?
A little bit, yeah.
The whole thing. I want the green table.
Oh, yeah.
Now? Okay. Okay, so the Mohs scale of mineral hardness is an arrangement of minerals by some kind of arbitrary set category, or what's the word I'm looking for? Some type of minerals. Some type minerals where we define the hardness of one as that of talc, the mineral talc. So it uses somewhat common minerals, what we call type minerals, and compares them, or it appropriates each of them a number, and then between those numbers are the other minerals. And so the minerals are, in order from least hard to most hard, their numerical values are 1 through 10. Talc, gypsum, calcite, fluorite, apatite, feldspar, quartz, topaz, corundum, diamond. And then this, if you go back and look at that table, you also see that some common objects, fingernail, copper, nail, glass, steel file, and streak plate, those things have a approximate hardness too, but the hardnesses are defined by those minerals. And so there are mathematical, like, science instruments that will measure the hardness of something with SI units, but usually we use the Mohs scale of mineral hardness. And we're going to go through these kind of fast because you'll learn more about these when you do your hands-on lab about identifying minerals. You'll know how to find hardness and how to find, what else? What other properties are there of minerals? Nope. Color. I'm going to put color. Color is a bad one. Don't use color. Color's a bad one. Almost any mineral can be black, and a black mineral could be almost anything. So color is not a good one. Sometimes, in rare cases, color is an okay way, but generally the color of a mineral is not a good way to tell what mineral it is. Streak is slightly better, because what streak is we use what's called a streak plate, which is an unglazed piece of porcelain, so it's kind of rough, and we rub the mineral on it, and the streak that it leaves behind it, the roughness of the streak plate powders it, and so instead of getting whatever color it's reflecting at us because of its smoothness, or we'll get to in a second, its luster, we instead get the color of its powder, which removes that luster from the equation, and we get a more accurate color of its streak, of its powder. So for instance, the mineral limonite can be black, as almost all minerals can be. It can be yellow, it can be green, it can be red, but when we streak it, it's almost always reddish-orange. Red, orange, yellow, green, blue, purple in the rainbow light show. Yeah. Light, shining colors in the rainbow, underwater rainbow. So luster, luster is how shiny it is, or what kind of shiny it is. There are different types of shininess. We usually break it down into metallic or non-metallic. I bet you know what those means, but what does metallic and non-metallic probably mean? No, it's all different kinds of shininess. But whether it shines like a... No, whether it shines like a what or not. Like a metal. So if it shines like a metal, that's a metallic luster. And if it shines in some other way, it's non-metallic. And within non-metallic, we have, if it shines bright like a diamond, that is an adamantine luster. You don't have to have these memorized. I'm just giving you examples. Adamantine means like a diamond. So gems have an adamantine luster. Have you ever seen a gem? Yeah. It's shiny, but it does not shine like a metal. Crystal gem. Okay, and then there's another one called glassy, if it shines like glass, which we sometimes call vitreous if we're feeling fancy, which we are. Vitreous. There's one, you'll like this one. There's one called greasy. It can have a greasy luster. It can shine like grease. You guys are being mean. There's also sometimes no luster, but we might call it a dull luster, or earthy, or pearlescent.
Man, there's a lot of lusters.
Iridescent. There's all different. There are a lot of lusters. But we usually, and in your lab, you'll break it down into either just metallic or non-metallic.
That's all we needed.
What other properties of minerals are there? What other properties of minerals are there?
Transparency.
Not really. That's not what we talk about very much. No, that kind of goes along with color. Try again. What other properties are there?
Smell.
No, we don't usually use smell or taste. No, those are terrible. Those ones are terrible. Okay, I'll tell you. There's one density, I hope you know how to find density. To find density, we find the mass, using a scale usually, of a particular mineral sample, and we find the volume usually by using a graduated cylinder with a certain amount of water. We slide the mineral in and measure the water afterward. That's how we find density. We sometimes refer to this as specific gravity. Specific gravity is just so that we don't have to use units with it. So what specific gravity is the density of whatever we found divided by the density of water. The density of water is 1 gram per cubic centimeter. And so if we found the density of our substance to be 5.3 grams per cubic centimeter, to express it in specific gravity would be to divide that by 1 gram per cubic centimeter, giving us an answer of 5.3. But now it doesn't have a unit, which is sometimes beneficial, so specific gravity we sometimes talk about instead. What other properties could a mineral have? You already ran out before I even told you that last one, so I'll just tell you the rest. Some of them... I'm sorry, what?
I said no.
Another one is cleavage, or cleavage and fracture. So cleavage is how this mineral breaks, breaking, how it would break. We don't have to break it to find it. Breaking along crystal lines. So remember, all minerals are crystalline, meaning they have a pattern of atoms. And some of them, let's say we draw mica. Do you remember mica from our field trip? Yeah. Mica's atoms look like this. Pretty strong pretty strong bonds in this direction and in this direction.
Like justice.
Yeah, pretty strong in these two directions, like justice. You can imagine that going on in more or less infinite. But then between the two layers of them, there's these weak, what I'm indicating with green bonds. Between the layers, there are these weak green bonds. And so the cleavage of this, what I've called mica, would be that along these, like in between the black ones, we would fracture it, where it breaks not along crystal lines. But if we peel it off along these green ones, that's cleavage.
Mica.
The way the mineral cleaves is the root word there, which means breaks. The way the mineral cleaves is along its crystal lines, and if it breaks in some other direction, that's called fracture. And minerals can have what's called perfect cleavage when they actually break fully along these lines, and they can have that in up to 3 dimensions. There are 3 dimensions of space, and so it can have X, Y, or Z cleavage. Some minerals have no cleavage, like quartz always fractures. The mineral is equally strong in all directions, and so it just fractures. And some minerals have perfect cleavage in 3 dimensions, like diamond does. And we talk not only about whether it has cleavage or not, but also about the angle of that cleavage. And so for something like calcite would have 60-degree cleavage in one direction. And that gets at the most important way, the best way for us to identify minerals is by their crystal form. A mineral is defined as what its properties, what its composition is and how those are arranged. Its composition and the arrangement define what that mineral is. So whether it's pyrite or diamond is defined by what it's made of and how it's arranged. And so if we can find out how it's arranged, the crystal form, that will tell us what mineral it is. The best way to do this is to take a thin section of either rock or a mineral, and then we look at it in a microscope and we see how the crystal lines, the cleavage shows in the microscope. That will almost definitively tell us what mineral it is. The crystal form is the gold standard, but it's kind of hard to identify in the lab, and so we use all these other ones along with it. We can't just get out a magic magnifying glass that will say, that one's pyrite, or even, that one's made of iron sulfide. We have to find the composition using these ones, and the crystal form usually using cleavage. Do you have questions about any of the properties of minerals? Do you have kind of a vague understanding of how we might use them to tell minerals apart?
Yeah.
What would be a good starting place?
The most hard.
Probably the hardness scale and streak are pretty easy. And then if there's still confusion, we might try to look at the cleavage and density. Sometimes the cleavage is the easiest thing to identify. Like in this mica, we're like, oh yeah, I can tell because of the cleavage that that's mica because of the way it is. Yes, Hunter?
With the hardness scale, that's probably
Mica.
I can't hear it. In between me and the guy asking a question is 2 other people talking for no reason.
in harder minerals like diamonds. I'm sure they found out that was the hardest by rubbing them.
Just rubbing them, yep. Okay, yeah, most likely. I mean, the most scale mineral hardness is just, I should have identified this earlier to you. Things higher on the Mohs scale of mineral hardness will scratch things lower than. And things lower on the mineral hardness scale will be scratched by things harder than. That's how we test them. We don't keep just a pile of diamonds to test whether it's harder than diamond because that's the hardest one.
You don't.
I don't. I don't, yeah. Yeah, you have to use your grill. What?
You rub 2 diamonds against each other?
They will scratch each other, yeah. That's how diamonds are cut. That's how diamonds have historically been cut. Nowadays, diamonds are usually, I think, I could be wrong, but I think they're usually cut with lasers. But before, when diamonds were cut, they were usually just cut with other diamonds, what are called industrial diamonds. Hey, this will be just a little side dish. It doesn't need to be cut. You can use a diamond just right out of the ground to cut things. This is a little side dish, but how do you think minerals form? There's 2 ways that minerals form. This is not hard, so please, you're doing one in the lab right now.
Like tectonics.
No! Well, that's almost like the second one, but which one are you doing in the lab right now?
Crystallization.
Yeah, okay, they're all called crystallization. That just means the process of forming a crystal. How specifically are you doing that in the lab?
Water.
Okay, what's happening with the water? The water itself is, no. What is the water doing?
Wet.
No, what is the water doing as you're...
Dissolving borax. Wet.
It dissolved the borax.
Wet.
It dissolved whatever you dissolved in it, and now the water itself is going to
Mix.
going to.
What?
the water has already mixed. What is the water now doing over the course of a week? Say it loud. Evaporating. Evaporation.
Oh.
So the water, thank you, Haley. The water is evaporating, leaving behind what was dissolved in the water, and as that happens, it will crystallize. Now, a really key part of this is not kind of the point of this chapter, but we'll talk about this in the future. The longer it has to do that, the longer either of these things takes to occur, the bigger the crystals get. Kind of like, have you ever had a cat?
Yeah.
If you have a little beautiful baby kitten and you kill it right then, it doesn't grow any bigger. The longer it has to grow, the bigger it gets. Right? If you have a 1-day-old kitten, it doesn't grow anymore. But if you have a 3-week-old kitten, it's a little bigger. And if you kill it then, it won't grow anymore. The longer it has to grow, the bigger it gets. Can you remember that? The longer a crystal has to grow, the bigger it gets. So the longer it takes to evaporate. So do we want to, would it give us really big, beautiful crystals if we did your lab and just boiled that water all off in 10 minutes? Nope. It would crystallize, but they would be tiny. So that's why we want to wait a week or a month or even years to grow the crystals, because they get bigger and bigger and bigger. What's the other way that minerals can form? So they can form from evaporation. No.
Heat.
Okay.
Hot. Magma.
Okay, yeah, cooling magma.
Hot.
Crystallizing or cooling from magma. These are the two ways that crystals form. This one's by far more common, the cooling magma, but that doesn't mean the other one doesn't happen. And it's also true for this one that the longer it has to cool off, the bigger the crystals get.
Bigger.
And so would a hot environment or a cold environment allow it to take longer to cool? A hot environment would have it take longer to cool. Yes, it will cool faster in a cold environment.
So with caves where there's stalagmites and stalactites,
Yep.
is that the water dripping and evaporating and forming a crystal?
Yep.
That's
Yep, and that crystallization actually happens really fast because it's just a single drop. So that's why when you look at a stalactite or a stalagmite, you don't see the crystals because they formed really fast, actually. They formed in the time it takes for one water droplet to evaporate. Okay, now the last thing is the categories. The last thing we're going to talk about anyway, the categories or just categories? I think it's categories.
Category.
I don't want that to be in blue, though. I want this one to be brown.
Let's just say columns.
The categories of mineral. The simplest category of mineral, well, actually, we're not going to talk about the simplest first. We're going to talk about, it's mostly broken up into silicate or non-silicate. The silicate minerals have something called a silica tetrahedron, which I actually have an example of it. It's in the lab right now. A silica tetrahedron is one silicon atom surrounded by, in 3 dimensions, 4 oxygen atoms. So this one with the kind of fat leg represents that it's actually like coming out towards us, and the dotted one represents it's going back into the board. In 3 dimensions, they're arranged so that there's 90 degrees between each of them. But this is called the silica tetrahedron. It's a polyatomic ion, SO4 minus, and it's called the silicon or silicate tetrahedron. And all of the silicate minerals have this as their base. There are different kinds of silicates. There are phyllosilicates like mica that are arranged in sheets. There are massive silicates like quartz that are just continuous directional arrangements of the silica tetrahedron. But the silicates all have this. And some examples of silicates, which I'll write in brown. The common examples are quartz, feldspar, mica. There are obviously many others. Asbestos is one, but these are the common ones. And then of the non-silicates, which don't have the silica tetrahedron, what do you think is the most basic kind of element? You're right, native elements, just elements. Give me an example. What thing from the periodic table could we probably find just crystallized all by itself in nature? Carbon, diamond, that's not super common, but diamond or graphite, carbon as diamond or graphite is a mineral. What else? Nope, oxygen is not a solid at room temperature.
Gold.
Gold, yep, not anymore, but back in like the Bible times, people would just be walking, they trip over just a lump of pure gold. That's all gone because people liked that. And so now we have to mine gold. But in a long time ago, there was just gold, not like everywhere, but there would be pieces of gold just around. Same with copper. Not really iron, but sometimes iron. Almost never, in fact, never ever aluminum. Aluminum's always combined. And that's why it was very rare to find pure aluminum. It wouldn't even be pure, but just metallic aluminum. And so you might have heard the story that Napoleon Bonaparte had aluminum plates for his very highest value guests. The cap of the Washington Monument in Washington, D.C. is aluminum because that was the most precious material at the time, because the process to get aluminum out of the mineral bauxite hadn't been invented yet, and so pure aluminum was extremely rare. What else? What other kind of non-silicate minerals are there? Well, I'll tell you. Oxides, sulfides, halides. There have to be more than that. Can you guess what? Can you guess what these might have to do with each other?
They're happening together.
Carbonates?
Oxygenizes.
No. They all have what in them, do you think? The oxides probably all have oxygen. The sulfides probably all have sulfur. The halides probably all have, do you know?
Alien.
No, you should know if you were ever in chemistry.
Paleontology.
Halogens. The halogens like fluorine, chlorine, bromine, and iodine. Carbonates have the carbonate group, or the carbonate polyatomic ion.
Like carbonate.
Sad.
And then they go.
Obviously, there are examples of these. We'll see some in the lab. Do you have questions about the groups, the categories of minerals?